All right, so in the last video, we talked about linear motion, and we derived the equations for describing the speed, velocity, and acceleration of objects that are undergoing linear motion. And now I'd like us to shift gears to a different kind of motion. And I want us to observe this image here that we have, and what is happening here? What is happening to the green and red ring? We can easily see that it is moving, right? And like we saw with the red brake, it is changing position, and it's along a circular path, right? And what direction is it going? It is going in a clockwise direction, like the way our clock moves. That is a clockwise direction, and it's at a particular speed. And so this could be going faster or slower. And we generally call this kind of motion rotational motion, and it's because the object is rotating about a fixed axis, and this is the axis of rotation. We'll call that the center, the axis of rotation. And we see this kind of motion in our robot wheels, the robots that we'll be using in this module. Robots or like cars rotate, the wheels rotate in order for us to have motion. And then we also see this in our homes, like on our fans, the blender in your kitchen, all have different variants of rotational motion. All right, so what I'd like us to do here is determine which of these objects is rotating faster. And I just don't want you to eyeball it and make an approximate guess. I'd like you to calculate the speeds and compare them together and find which is higher, has a higher speed. So take a few minutes and pause and replay the video as long as you like in order for you to be able to calculate the speed. Okay, so I hope you were able to try it out, and I'd like us to work through a solution together. So as we did before, in order for us to find the speed, we use a stopwatch to determine how fast, or the approximate time, I should say, for the object to complete one revolution. So one revolution is one complete rotation along this circle, and this is also rotating about a circle if you're looking at it from downward. So if you use a stopwatch, in this case, you can say you start counting when it crosses one point and then wait until it crosses that point again. And if you do that correctly, you get values that are approximately close to this. These are just approximate values. And with the time taken over one revolution, we use this formula, which is very similar to what we saw in linear motion. The average angular speed would be the angular distance covered over the time taken. And the distance in this case is how many times you rotate around, or you complete revolutions of the circular path, and then the time is the time taken. And so if you fill out this table, you have for object A, which is the fan, 1 over 2.5, which would be 0.4, and 1 over 8 would be about 0.125. And we can see these are scalar values determining the angular speed. We can also calculate the angular velocity, which would be an angular displacement over time taken. Remember, as we talked about before, that velocity is a vector quantity, meaning it has magnitude as well as direction. And so we have to find a way, how do we define direction for rotational motion? Well, the obvious way to think about it is this can either be moving this way or the other way. And in this example, this is moving this way, which we refer to as clockwise motion. And this is moving the other way, like you see my cursor, which is anti-clockwise motion. And so we would have results like this. ACW is anti-clockwise, and CW is clockwise. And so this is how we can calculate the angular speeds and angular velocities of objects. All right, so now we can summarize what we've learned about rotational motion the same way we did for linear motion by defining our relevant equations. So first we have the average angular speed, which we just saw from our last slide to be the angular distance covered over time taken. And to put it differently, we can see using some more Greek letters. This is the letter omega, which looks like a W. We use that to define angular speed. And this is the Greek letter theta, which we use to define angular distance, or like position. And so this will give us omega equal to change in distance over, or change in position, you can say, over change in time. And so this will give you average angular speed. The next equation is the average angular acceleration, which we should think about how it just mirrors the linear motion case. And so we have the very same formula, just using different notations. And so instead of a, here we have alpha to denote angular acceleration, and then here we retain our omega for angular speed or velocity. And so we have change in angular speed over change in time gives us average angular acceleration. So now we want to see how we can convert from rotational motion to linear motion. And this is very important because this is how our robot will work. We'll use some kind of mechanism to rotate the wheels of our robot, and that will drive the car or the robot forward or backward. And that's also the same way cars work. Cars have the engine causing some rotational motion on the wheels, and that drives our car forward or backward. So, but we want to see how does that rotational motion translate to linear motion, right? So I'd like you to take a few minutes to think about this and attempt this question. So the question is effectively asking you to determine how long would it take for this wheel. And so think about this as just a single wheel which is moving along this straight line. And this is just like middle position and then the final position. And so the wheel is moving from point A to point B, and the question is saying, how long will it take for the wheel to move from A to B if it is rotating clockwise, as you can see the arrow, at 10 revolutions per second. And you might not be familiar with this assumption that we have here, which is that the wheel doesn't sleep as it rotates. But don't worry about that for now. What it just means is that all of the rotational motion translates to linear motion. So pause the video and try this out. So what do we do first? Well, we state what we know, right? So first of all, we know from the question that the angular speed of the wheel is 10 revolutions per second. And here I'm using W instead of omega, but that is the same thing. So the angular speed is 10 revolutions per second. And then also, what else do we know? We know the radius of the wheel. We know the radius of the wheel is 0.1 meters. And so that's how wide the wheel is, 0.1 meters. And so how do we find how much distance is covered by the wheel in one revolution or one rotation, given these parameters? Well, you've heard of the term circumference of a circle. The circumference of a circle is the distance around the circle. So the circumference of the wheel will be the distance around the circular path of the wheel. And how we calculate circumference is by 2 pi r, right? And so the circumference of the wheel will be c, which is equal to 2 times pi times r, which is the radius. And so we'll have this value. And so now the circumference tells us that in one revolution around this wheel is 0.624 meters. And so if the wheel rotates along a straight path by one complete revolution, it will cover 0.624 meters. And so then if the wheel rotates at 10 revolutions per second, or 10 revolutions in 1 second, how much distance will the wheel cover in 1 second? And so at that speed, the wheel will cover 0.624 times 10 meters in 1 second. And so the wheel will cover 6.24 meters per second. And so so we have the value as the distance that is covered by the wheel in 1 second. based on the speed and the radius. And so what does this mean? So what this means is that the linear speed of the wheel rotating at 10 revolutions per second with the radius of 0.1 would be 6.24 meters per second. And in other words, it is how fast the wheel is rotating along a straight line, which is why we have it as a linear speed, or how much distance is covered along a straight line per second, and that will be 6.24 meters per second. And if once we have that, we can easily calculate how long it would take for the wheel to reach B, which is 10 meters away from A. And easily that will be the distance, which is 10 meters over the linear speed, which is 6.24, which will give us 1.602. And so this shows how we are able to convert from rotational motion of the wheel to linear motion of that same wheel, assuming that there's no wheel slippage, like we assumed at the beginning. So there's a more formal equation that defines this a bit more elegantly, and it looks like this. And what we have here is v is the linear speed, r is the radius, and omega here is the angular speed as we saw before. And if you use this same formulation to respond to this question, you get the exact same value. And so r will be 0.1. Omega here in this case would be not exactly this omega, because this omega is in revolutions per second, whereas our value here should be meters per second. And so you'll be multiplying 10 revolutions by 2 pi in order to get into meters. And then once you do that, you would be able to just multiply them out together. So effectively, this is what we have done here using this more formal equation. And one other thing is that you observe that these quantities are all scalar, right? We have angular speed, linear speed, and this formula can be defined in the vector case as well, but we'll not be covering that in this video. I'll add some comments on that in the additional resources for those who are interested. And so we find this concepts to be very important when we are designing a robot, as well as when we are writing control programs for our robots. All right. So what did we learn in this lesson? I hope that this was a recap for most of us. And also, I hope that those who are being introduced to this concept for the first time found this lesson to be accessible. So first of all, we talked about linear and rotational motion. We then looked at the difference between scalar and vector quantities. We did some exercises for calculating distance and displacement. And we then considered and calculated speed, velocity, and acceleration of both linear and rotational motion. So the linear motion that we discussed in this lesson was just for one dimension, which is sufficient for this level, but we have additional resources which discuss linear motion in 2 dimensions. And then we finally looked at the conversion of motion from rotational to linear, which is a very important part for robotics, especially for mobile robots. The reverse, which is from linear to rotational motion, is much less common, and we did not discuss that in this lesson. And so thank you for watching this lesson, and I would encourage you to look over the additional resources that we'll be providing if you have any further doubts.